Greetings, peeps. We're doing the FullBola, a problem that involves sports, which is kind of cool. We can actually make this applicable to something. In this case, the sport is known as American football kickoff, right? So at the beginning of a game, or after a touchdown, something like that, a pair of lips is kicked by a place kicker. What? Pair of lips. Yes, check it out. Look. There they are. Way to the left of your screen. Okay. We'll go back out. They do look like lips. I just noticed that. That's pretty. Football kicked by a place kicker at an angle of 40 degrees with respect to the ground with an original velocity 22 meters per second. We want to find out the following. What is the max peak height of the ball? What is the ball's total time aloft? And the horizontal range of the ball. Okay. So what we're going to do is, of course, create a drawing, which I've already done, but we'll do all the scratch math together up here. So some of the data that I carried from the problem was the initial velocity, original velocity of 22 meters per second, the angle with respect to the ground, which is the horizontal, 40 degrees. So you got to make sure, again, your calculator sets degrees, very important. And so the drawing starts like this. We have our lips that are over here, kicked at an angle theta with a velocity v naught. So the strategy is kind of interesting. We can see, though, that, of course, this is going to make the FullBola over here and land. But in order to tackle this problem, it's really difficult to do this when your angle changes. See, this angle would get smaller until 0, and then it would increase on the way down. And it's really hard. You would need some calculus to evaluate it that way. But we've got some techniques using the equations of motion and our knowledge of gravity to be able to handle this situation. And the strategy is to use trigonometry and to break up this initial velocity, original velocity, I call it either way, into its horizontal and vertical components. So what that means is, because this is being kicked at an angle, it's moving both vertically and horizontally simultaneously. Okay, at the same time, we're moving horizontally and vertically. So there's some part vertical, some part horizontal, kind of like the north and east. You can go northeast. So in this case over here, we have one component that's v naught x, and the other component is completely perpendicular, and that's v naught y. And the reason why we like to use perpendicular is because we have the trigonometry to deal with it, but also because gravity only acts in the vertical direction and doesn't interfere with this over here. So it's kind of neat to do. We also have our max height here, which I'm going to call dy. At that max height, the v peak is 0 meters per second. We still have, though, a horizontal velocity that's the same. That never changes throughout the flight because there's no air resistance. We're ignoring that. And there's no horizontal gravity. No horizontal gravity. V naught x. Down here it lands, and we have, again, some components. Before we created the components, now, or we had the components and we got v. Over here we're doing the opposite. We are going to find the components from our initial velocity v naught here. It turns out that v has the same value as long as we kick the ball and land at the same height. So this is 0 meters here, if we want to make that our reference. Because of the symmetry, this v will have the same value, the same magnitude, and the same angle over here as up there, okay, as the beginning. So this angle here will be the same as over here. Of course, not drawn to scale because I'm not that great at drawing, but easy enough to picture. All right, so that's your situation. So again, what we're going to do is we're going to tackle this with our grid of motion variables, the 2D motion variables, and see what we can fill in. So we'll slide this puppy over, like so, and let's see what we can do, guys. All right. Well, what we know here are just two values, which is pretty interesting. What is amazing to me is that two simple values, in this case the angle and the original velocity, can give us a whole bunch of other ones. That's all we need, and then some knowledge of physics beyond that. But for these two values, we get a whole host of other things, which is pretty cool, I think. I noticed that the lighting is so much different. I think it's so much cooler, so much nicer when I put the blackboard here versus the reflection of the dry erase board. I just am more full of life, more the vita. But we're gonna have to move it away, unfortunately. But I do like it. Maybe I should get more chalkboards to draw with. I think it really shows. Hey, what's our angle? Our angle theta was 40 degrees with respect to the horizontal, 40. Our V naught was 22 meters per second. I'm pretty sure I didn't mix these up. I got that all right. It's the same example, by the way, that's in your book. It looks like it starts on, let's say, page 68. Yeah, so if you wanted to follow along. They diverge in technique a little bit, but it's the same idea. And again, when there are multiple ways to do things, that is a powerful, powerful item. We like that. We can already write down the velocity of, it's 22 meters per second, but with an angle here of negative 40 degrees. And so this would also be 22 meters per second because it's going to be a symmetrical problem. All right, here's what we do. The strategy now is to find the horizontal original velocity and the vertical original velocity using the trigonometry. Okay, based on that triangle, and I'll draw the triangle out. We have the cosine of the angle related to the horizontal side, and we have the sine of the angle related to the vertical side. Let's draw that out before we return this and work out with the values. Okay, so we have 22 meters per second here. All right, and this is our V naught. And I want to stay consistent with the colors. We've got over here V naught x. And notice that if this is the angle, here, this is the adjacent side. I'm going to write SOHCAHTOA in the way that we saw it before, with the interesting kind of script like so. SOHCAHTOA, SACAHTOA, kind of maybe that's just how things are written in different places. Why not? Okay, theta's over here. Well, what is our V naught x? What we got here is V naught, the hypotenuse, times the cosine of the angle. Okay? And the reason why is because if we look at it over here, there's a relationship between the adjacent and the hypotenuse. We solve for the adjacent, and it would be the hypotenuse times the cosine of that angle. All right, so what is that value? Well, we've got 22 times the cosine of 40 degrees. And that equals, let's see, 40 cosine, I'm in totally in degrees, 40 cosine 22 cosine 40. Want to see if you were paying attention. 22 cosine 40 degrees. And we got about 16.85. All right, that's fine. I bet your book will round it. I could just look here, right? But I wanted to do it for myself. Oh, they just rounded to 17. Beautiful thing. Why not? Let's go. So this is about 17 meters per second. So the amount of horizontal velocity is 17. What is the vertical velocity? Well, we're going to set that up using a little trig. Here we go. So we got V naught y equals V naught times the sine of the angle here, and that is 22 sine of 40 degrees. Okay, and that equals about, I think, 14, if I remember right, because this time I looked, I could punch it in the calculator, but hey man, I got the thing right here, 14 meters per second. Okay, you could try it out yourself. Make sure you do get these values, 14 and 17. So, hey, this makes a little bit of sense. Let's think about it. All right, a little gut check here. If this is 40 degrees, then it's a little closer to the horizontal because we have a right triangle or a right angle of 90 degrees, which means that halfway would be 45. In that case, they'd be equal. But at 40 degrees, this vector is a little closer to this guy over here. So we got this value being higher than that value, all right? The one that's closer to the side which is larger, 17, because the angle's lower here. So that totally makes sense, all right? So that's our little gut check to make sure that we did the calculations okay. Now, let's transfer them to the board over here, all right? So now we've got V naught y, which is 14 meters per second. And we have V naught x, 17 meters per second. Excellent. So the first question was asking us how much time was the object in the air? No, it was peak height. Hey, let's go look for a moment over here. What does it say? We're gonna have to answer both anyway. Oh, peak height of the ball. All right, we're gonna find the peak height. So height obviously means vertical, and we're gonna spend our time over here at the vertical side. All right, so let's see what we've got. So one of the established values over here that got erased, 9.8 meters per second squared. We'll put that back. All right, we should be able to find d from these values over here. So let's see if we can find an equation that will do that, okay? So I'm going to scratch this stuff and work all vertically. Now this time I really don't have to find, Vy and other stuff like that. Like before, when we did the FullBola, it seemed advantageous to do all the calculations of the vertical side first, and we kind of went back and forth. But in this case, shouldn't be so bad. All right, so we got V naught y is 14 meters per second. Well, we also know that the peak is 0 meters per second, okay? And we also know that AY is equal to G, which is equal to, according to our coordinate system, negative 9.8 meters per second squared. All right, and we want D, Y. Okay, well, this is as if I were throwing an object upwards at 14 meters per second, and we wanted to figure out the maximum height. So we've done problems like this before in one dimension, just throwing an object up. And so we can find an equation for this. And I think because we don't have time, the obvious choice is the fourth equation. So that looks like this. So we have Vy squared equals V naught y squared plus 2ay times dy. Beautiful, because we have 1, 2, and 3, and we're solving for that. All right, well, let's do this. We already know that one of them is 0, hey, so let's just kind of zap that for a moment. This is all 0. And so what we have is negative V naught times y squared over 2ay, which is g. All right, I'll just write that down. I'll substitute it right now. 2g, like that, equals dy. Beautiful. Okay, so what were these values? Well, we got 14, so we have negative 14 squared. Now the negative's outside, so it's kind of like this. Negative 14 meters per second squared over 2 times g, which is negative 9.8 meters per second squared, according to our coordinate system. All right, so let's try that. I kind of want to calculate it. So I want to make sure that my answer is the same as the book this time. And 14 squared and divided by 2 times 9.8. And I got bloop, 10. That's what it is. That's the answer, actually. So they designed it to be a nice, clean answer. Hey, the max height is 10 meters. Beautiful thing. We're going to populate our board and move on to the next thing. Because maybe that value actually comes in handy. It certainly could. Okay. Here we goes. We got our board back and the beautiful lighting. And dy is 10. 10 meters. Okay. I could certainly find Vy. I'm not going to do it to save time because really it's not asked for unless we were looking for it for a particular reason. So that's fine. Okay. So now we got all this information over here. We want to find time and then of course share that with the horizontal side in order to get the range. So we're going to get t peak and t total. In this case, because we're talking about the hyperbola, the t peak is going to be up to the shot from the ground up to the peak, and then because of symmetry, t total is just going to be double that. So it's going to be pretty easy. All right, so we're going to try to solve for t peak using the vertical side right here. All right, so I'm going to slide this, and I'm going to be able to write those values, and then move the board down. Let's just get this erased over here. All right, part of it anyway. All right, so we got dy equals 10 meters. V naught y is 14 meters per second. We have V y peak is 0 meters per second. Ay equals g equals negative 9.8 meters per second squared, again because of the negative because of our coordinate system. And now we've got a bunch of information we want to find. T. All right, and sorry, I'm going to be very specific here, T peak. All right, so that's what we're looking for. Let's put this guy down again and give us some space to work. All right. Goodbye, 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 goodbye. All right, well, hey, I think there's a really simple equation, actually. Funny thing is, we probably didn't even need to find the dy in order to get this. It's kind of nice to have. But check this out. We have v naught y, vy peak, and ay. So you know what? To get t, that first equation is going to do us really nicely. Because here it is. It says vy equals v naught y plus ay t. Solving for t, right? Well, let's see. Is anything 0 that we can knock out? Yeah, this would be vy peak over here. Okay, so that's 0. So we have negative v naught y equals over t equals ay, which is g, like that. And that's going to be negative 9.8. So, hey, why did I solve for that? Silly me. I want to solve for t, so now we put this over here like that, g as such, and so we have negative 14, right? 14 meters per second divided by g, negative 9.8 meters per second squared, and that's t peak. T peak. All right, so looks like it's like 1.5 seconds or so, and hey, sometimes I won't feel like calculate it. Sometimes I'm not going to calculate it, but this time I will. The book goes about this solution a little bit differently. They actually calculate it over the full parabola. It's a different technique, and it's fine, but it's a little tricky, and you're free to use this for a symmetrical problem. I also will go into situations that are not symmetrical, and we'll have to use, sorry man, I think we'll have to use probably the quadratic equation. So anyway, I got about 1.43 here. So we got 1.43 seconds. So that's the football. No more ellipse, that's actually football. To the peak and the t to get there. The time is 1.43 seconds. Guess what? Time to put that in the information board because we're almost done. We're going to get the range and then we're going to celebrate, and hopefully it was a good kick. All right, t peak. Hello, t peak. 1.43 seconds. Like so. T total is going to be double that because of the symmetry of the problem. So 2.86. So it's going to go, instead of up to the top, it goes up the top and then back down to the ground. Time up equals time down. We learned that on the sports clip, right? FSM sports clip. Okay, now that we've got time, we can share that with the stuff over here. All right, so it's dx that we're looking for. This is the range. And we're going to use t total for that because that's the total time this object was in the air. So let's see how to do that. Well, it's simple. Remember we chose the third equation last time in the half-load problem. So I'm going to write down real quick again just as a reminder. So it's dx, which is the range, equals v naught x times t plus 1/2 ax t squared, and ax is 0, no horizontal gravity. So here's it. It's just v naught x, which before we determined to be 17 meters per second. So it's 17 meters per second times t total, all right? In this case, total. And that was 2.86 seconds, okay? And I'll do that really, really quick. 2.86 times 17. Simple calculation. 46.5, we'll call that 49 meters. Why not? Pretty close. So the range is about 49 meters. That's a pretty hefty kick. That's a far kick, I think, as far as it goes. Certainly depending on the level. All right, so that's our range, and I'll populate that, and then it's story time. What's our discussion statement, basically? It's lots to say at this point. We have so much more richness and detail. So those one-sentence things that we've been doing before ain't gonna cut it. We got to write a paragraph at this point. So the D was 49 meters. That's the horizontal range, the horizontal displacement from the kick. All right, now we've got the story. So we started off with a kick of 22 meters per second at an angle of 40 degrees. And the ball will be in the air for 2.8 seconds in total. It reaches its peak at half that time, 1.43 seconds. The horizontal velocity is 17 meters per second. It will make the whole range, the whole range of this kick is 49 meters, so hopefully somebody's down there to catch it or something. I guess that would be the opposing team though, so maybe they position themselves to do that. And what's the max height? Okay, so this ball also, when it hits its peak, reaches a height of 10 meters. Now things get more interesting in the story when we have some type of a goal. Maybe it's a field goal problem, or maybe it's a problem where there's a home run where we need to try to calculate, and the story would be the ball either makes it in the field goal or it doesn't. We would just go with the two-dimensional piece and assume that the angle is all right on, but is it going to reach in terms of its velocity? Is it going to be far enough, high enough over the bar to do that if it's a straight-on kick, or if it's a home run is a pretty good example of that. So those are the types of problems we can do. So there's tons of story there. Is it a home run or is it not? Is it a field goal or is it not in terms of what we can calculate? All right, beautiful thing. So with that being the case, bid you farewell. Morad out.